Hello viewers, welcome to the massive open online course on engineering mechanics. Today we will start the module 12, that is on kinetics of rigid bodies, and main topic will be on planar dynamics of rigid bodies. This is the unit 1. Now, what is the importance of this planar dynamics of rigid bodies? Actually, in many engineering applications, what happens, the actually rigid body consists of number of particles. So, each particle of a rigid body, when it moves in a curve which is a planar curve and which is parallel to a reference plane. So, this type of situation are dealt in this planar dynamics, and for analysis what happens, the motion of the body may be viewed within the reference plane and all forces and moments acting on the body can be projected onto the plane. Now, what we will cover in this unit, that is we will first introduce the force linear momentum relation for a system of particles, then moment angular momentum relation for a system of particles, then we will derive the equations of angular motion for a rigid body rotating about a fixed axis, and derive the equation of motion for a rigid body in general planar motion, and after that we will apply the equation of motion for rigid bodies in translation, rotation about fixed axis and in general motion. Now, as already I have told you that for any rigid body it consists of a large number of particles. So, first we will deal with force linear momentum, that means when a body is in linear motion, what is the relation between the force and linear momentum. So, what we will do, we will derive the principle for n number of particles and then that we will generalize for a rigid body. So, let us consider the system of particles which consist of n particles, and this its position vector, it has large number of particles. Let a particle is ith particle whose mass is mi and its position vector is ri from a point fixed point on the inertial frame. Now, using the Newton's second law, we can write on this for this particle the Newton's second law, that is on this left side of the equation 1 we can see that what are the forces acting on the particle I, and right side what is the rate of change of momentum. Left side the first term is f I j and sigma of f I j for j equals to 1 to n, that means f I j means on the force exerted on the ith particle by the jth particle, and f I e is the external force on the ith particle. So, these are the forces exerted on the particle I, and due to this particle's ith particle's mass is mi and its velocity vector is vi. So, mi vi equals to the momentum, so linear momentum. So, rate of change of linear momentum equals to the applied force, and this velocity vi equals to, if ri is the position vector, so d ri dt is the vi. Now, with this equation number 1 is applicable for a single particle, ith particle. Now, if we sum up this equation for all the particles, n particles, then this sigma I, sigma j, f I j plus f I e equals to d dt of mi v I. So, for n particles if we write this, then on further simplification we will see that this for in the left hand side f I j, there will be always some, for each term there will be a negative equal in magnitude and opposite in sign term will be available. So, what happens, all the terms like in f I j you will get f 12, f 21, f 13, f 31. So, f 12 and f 21 their magnitudes are same, because these are the action and reaction, because ith particle exert force on jth particle and jth particle applied force on the ith particle, these are action and reaction. So, these are equal in magnitude, but opposite in direction. So, F12 and F21 will cancel, similarly F13, F31 will cancel. This way this term will be sigma I sigma j f I j will be 0. So, further we can this earlier equation 2. So, first term becomes 0, second term we can write as sigma f in this. So, in equation 3 we can write that sigma f, that means total external force applied on the ith particles equals to rate of change of momentum of the ith particle. Now, what happens? So, m equals to, that means mass of the particles, total mass equals to m equals to sigma m I, and position of the center of mass of the system is, because m I r I for each particle the mass is m I and r I is the position vector. So, this way we can find out the center of mass of the system of the particles, and velocity of the center of mass equals to dr dt, again it is equals to sigma m I v I, I equals to 1 to n by m, we will get the velocity vector of the center of mass. This way we can, earlier equation we can simplify as sigma f equals to d dt of m v, that means m is the mass of the center of mass of the particles, mass of the center of mass, that means total sum of the masses of the particles, and v is the velocity of the center of mass. So, this way this equation we can get. Now, so here we can see that the total external force on a system of particles thus equals the rate of change of the product of total mass of the system and the velocity of the center of mass. So, if we go to the earlier center, that is sigma f equals to d dt of m v. So, here m, as m is constant, so d dv dt equals to acceleration. So, that we can see here that sigma f equals to m a, mass into acceleration, dv dt equals to a. So, this is the first case, that force and linear momentum relationship. Now, we go to the another case, that is when we want to find out the number of system of particles are there, and we want to find out what is the effect of the relation moment angular momentum principle. That means, moment we find out about a point O in the inertial system, that point is fixed. Again the same r I is the position vector of ith particle, and here r particle and r I is the position vector of the center of mass. In the earlier section we have already discussed that r is the position vector of the center of mass. Now, here another term in the figure we can see, r I is the position vector of the ith particle, that is whose mass is m I, and r vector r is the position vector of the center of mass. Now, from the center of mass to the ith particle, that relative position vector is capital R I. So, this is the position vector relative capital. Now, so already that by Newton's law, whatever we have written the equation, that equation can be multiplied by cross, that is if we do the cross product by r I on both sides, then we get this equation. So, and we you multiply the Newton's equation, we cross that is cross product of the Newton's equation by r I and take sum of for these n particles, then we get the equation 6. Now, this equation 6 how to simplify? Actually r I cross r 1 cross f 1 2 plus r 1 cross f 2 1, if we simplify we will see that this earlier equation, that is first term r I f I j sigma I sigma j, this will become 0 here, because for action and reaction their moments will be equal and they will cancel each other, because action reaction forces are equal in magnitude, but opposite in direction, and their R I, if you take the cross product, their value will be same. So, they will cancel each other, that way first term will be 0. So, second term will be there. So, now we can again we can see that second term will be R I cross F I, that means this external force applied on the ith particle. So, what will be the moment about the O? So, if we take sum of all the moments acting on the particles, it becomes capital M 0, and right side, another thing is right side R I cross M I V I d d t of R I, this thing we write like this d H 0 d t, where this H 0 equals to R I cross M I V I. So, this sigma, this is H 0. So, this is the total angular momentum about O. Thus, the sum of the moments about O is equal to the rate of change of total angular momentum about O. So, by using equation 4 and 5, in equation 8 we can write m 0 equals to d d t of r cross m v plus h. Now, here the significance of this thing is two things, that this total left side is the total moment about the point O, right side actually two parts we can see, r cross m v and h. This r cross m v is the momentum of the center of mass, about the center of mass, angular momentum, and second part is h equals to r I m I. So, this is actually of all the particles, r I is the position vector from center of mass to that particle, ith particle. So, this way we will take, and only center of masses momentum, that momentum we can find out from this first term, that is r cross m v. So, this way two parts are there, but when this r is equals to 0, then the center of mass and the original point, that is point O, are coincided. So, there we can write sigma m equals to d h d t. So, H 0 already what I have explained, that H 0 total momentum about O equals to two parts. One is, that is the first part is for the particles about the center of mass, and second part is the momentum of the center of mass about O. So, this we have already explained. Now, we are going to find out another thing, equation for angular motion for a rigid body about a fixed axis. Suppose a rigid body is rotating and about a fixed axis, this axis is L 0, and now we align the axis of in such a way that the z axis of the z axis, which is fixed to the rigid body, aligns itself with the L 0. So, z direction. So, now what happens, the rigid body is rotating about L 0, that means it is rotating about the z axis. So, its angular vector omega will be omega k, k is the unit vector in z direction, and the velocity vector of the ith particle of the rigid body equals to d r I d t equals to omega cross r I. So, omega we know, omega this angular vector equals to angular velocity vector omega k cross r I. So, this momentum moment magnitude of moment, we can find out the moment vector cross k dot k, k is the unit vector in the z direction, that way we can find out the moment about the z axis. So, we know that already earlier we have found out that sigma m 0, that means total moment about O equals to d h 0 d t, where h 0 equals to h 0 k and h 0 k equals to this r I, h 0 already we have found out. So, if we use the earlier equations, we can get this thing r I cross m I, then omega k cross r I, dot k. Just from H0's expression from earlier equations, if we put, we will get this thing, and here the triple product rule we apply, then it will be simplified to H0 equals to mi k cross r I square, because it becomes a scalar quantity into omega. So, this is the magnitude of the H0. Now, in this case this k cross r I, now what happens when it is rotating, the r I is the position vector of the ith particle from the z axis or L0 axis, whatever we call. So, this k cross r I actually gives the perpendicular distance from the particle to the axis of rotation. So, that way we get the r I, small r I is the distance, perpendicular distance of the particle from the axis is r I. From this cross product we can find out. So, this with this value we can find out the moment of inertia of this particle I 0 equals to, if I take the sum up of each particle m I r I square, we can get the moment of inertia. So, H 0 becomes I 0 omega. I 0 is the moment of inertia, omega is the angular velocity. So, this is the angular momentum. Now, if we want to find out the angular motion of a rigid body about a fixed axis, we can use this relation. Ultimately we got that m 0 equals to I 0 alpha. Now, we want to another case we are considering, that is equation of a angular motion of a rigid body. In this case this is the similar case whatever already I have told you, but in this case what happened, another axis we take. L 0 is already an axis through O and perpendicular to the plane of rotation. L is another line, another axis parallel to L 0, but passes through the center of mass of the rigid body. So, the rigid body's angular velocity vector can be expressed as omega equals to omega k. So, now this r I is the, that means from center of mass to any particle I we have already denoted by capital R I. So, d r I dt equals to omega cross r I equals to omega k cross r I. This way we can find out. Now, by taking the product with k, we can find out the value of the moment. So, m 0 equals to, this is about moment about O equals to d dt of r cross m v dot k plus h, which I have told you that two components are there. So, this we can find out. So, h equals to h dot k is the angular momentum about L. Using the same identity applied in earlier equation, we can find out that h equals to, we have simplified earlier. So, here for small r I you have found out, here for capital R I you are finding out, that means k cross r I dot square into omega. So, I equals to m I r I square for rigid body about L, and so body's angular momentum about L is h equals to I omega. So, the substituting in this equation 18 we can find out m 0 equals to d dt of r cross m v linear momentum, then we dot product. So, we can get the magnitude and I omega. So, that means about the C g, and this is the center of masses actually momentum we are find out. So, this way we can find out the two parts of this thing. So, from these things actually three basic equations we have got. That means, let us now what have happened, two axes we have already told you, that L and L 0. So, m 0 if r equals to 0, that means distance between the point O, fixed point reference point O and the center of mass is 0, then m 0 becomes m, then at that time sigma m, that means the moment, total moment equals to moment of inertia about the center of mass into angular acceleration. So, this we have found out. So, here mainly for this planar motion, actually 3 equations we will use for solving problems. One is Newton's second law, that is sigma f, sum of all the forces equals to m into a is the acceleration. Another is if a rigid body rotates about a fixed axis O, total moment about O equals the product of inertia about O and angular acceleration. So, m 0 is the moment about O, I 0 is the moment of inertia about O, alpha is the angular acceleration. So, this relation also very useful, which we have already found out. And another equation we have found out, if the total moment about the center of mass equals to m and the moment of inertia of the center of mass and the angular acceleration is alpha, then m equals to I alpha. So, these 3 equations we will use, and with this actually equation of motion, by this we can solve the planar problems. So, here normally the steps we follow, first you have to, for solving any problem, draw the free body diagram, that means isolate, when you draw the free body diagram, isolate that object and identify all the external forces and couples which are acting on it. Because when you are detaching another body from this particular body, so what that effect is shown by these forces and moments applied on this. Then apply the equations of motion, which you have already learned now. So, those equations we will apply according to the applicability. But with this we cannot manage, because the number of unknowns will be more than that. So, we have to get more equations, relations, for that we can get from kinematic relations between the variables. So, there are if suppose in this case, just one case is shown here, this body actually moves in horizontal motion. So, it is a translatory motion. So, in this case the condition is sigma m equals to 0, the total moment equals to 0 on this body applied forces, and total moment on this body is 0. So, with this condition we will use to find out. So, here Newton's law will be applicable in this case. So, sigma f equals to m a, this rule will be used. Now, we are going to one problem we are seeing. So, here is an aeroplane. So, 2 wheels are shown and there are supports. So, 2 wheels are supporting forces at A and B, and there is one thrust force due to the thrust force of the engine, and this thrust force is 700 kilonewton and the aeroplane's mass is 250,000 kg, and we have to find out what are the normal forces, that means at A and B what are the normal forces exerted by the ground on the plane. So, how to proceed? So, our approach will be during takeoff roll, the aeroplane is in translation. So, the sum of the moments about the center of mass will be equal to 0. So, using this condition and Newton's law, the acceleration of the plane and normal forces exerted on the wheels can be determined. So, here this horizontal component of all the forces we just write f sigma f x and sigma f y. Here aeroplane's weight and 2 wheels, 2 forces A and B, they will balance the weight. So, A plus B minus m g equals to 0, and the thrust force T equals to m a x is the acceleration of the plane. So, this way we can, from Newton's law we get 2 relations. So, from this we can find out the a x. Now, equation of angular motion, again as it is a translatory motion. So, sigma m equals to 0. So, in this case from this we can find out the supports at A and B equals to, by solving these equations, 2050 kilonewton and B equals to 402 kilonewton. So, here the object is in equilibrium and already it is given that the sum of the moments about any point due to the external forces and couples acting on it is 0. When a translating rigid body is not in equilibrium, we know that the sum of the moments about the center of mass is 0. So, by using this we have found out. Next, another case is how to analyze the motion of a rigid body about a fixed axis when it is rotating about a fixed axis. So, already we have derived. So, this equation we will use m 0 equals to I 0 alpha. That means, we have to find out the moment of inertia of this body about point O and angular acceleration alpha. By this we can find out. So, this equation is used. So, here let us one example we have taken. Here is a crate, it is being lifted, pulled by a winch. So, this winch, that wheel, there is a rope is there. So, rope is crate is pulled by the inclined surface. So, the inclined surface, this winch is pulling the crate, and the mass of the crate is 45 kg, and the dimension B, that means center of the wheel to the rope is B, and the coefficient of friction between the crate and the surface, inclined surface, is 0.4, and the moment of inertia of the drum on which the cable is being wound is I a equals to 4 kg meter square. If the motor exerts a moment of m equals to 50 Newton meter, what is the crate's acceleration? This we have to find out. So, again here what will be the, already we have shown the 3 steps are there. You have to first draw the free body diagrams, then you have to write the equation of motion, and then we have to kinematic relation we have to develop, because some additional some more by this equation of motion, actually less the number of unknowns will be more than the equation of motion. So, these additional equations required we get from the kinematic relation. So, here what first we draw the free body diagram. So, what are the forces? They are shown here. In the case of crate, the inclined surface is giving normal force is N, frictional surface as it is pulled upward. So, the frictional force will be leftward, and the this drum is also rotating. So, there is a tension T. So, due to that some moment will be created. So, this way we can and it has a weight also. So, all these components are shown here. So, this way we draw the free body diagram. Now, equation of motion, when we will write just for the equation of motion for the crate. So, on the crate f x and f y, we take all the forces and equals to m into x, Newton's law, second law we apply. So, f x equals to this much, f y equals to n normal force minus the component of the weight equals to 0, because it is balanced in that direction, there is no motion. So, it will be 0, and the equation of angular motion for the drum is m a, the total moment, equals to m minus b t, tension is there, motor moment, motor is applying some moment m, and b t is the due to rope tension is T. So, due to that whatever moment is coming, that is creating the I a is the moment of inertia about the axis A, alpha is the angular acceleration. So, this way you get the 3 equations. So, 3 equations for 4 unknowns. So, here we have 4 unknowns. So, how to get the another equation, otherwise 4 unknowns we require 4 equations. So, this is from kinematic relations we can find out. So, okay, first we simplify these things, next we go for kinematic relation, that is angular acceleration of the roller, that is winch roller, and the linear velocity of the crate, this we can relate. So, linear acceleration of the crate equals to a x, and angular acceleration of the roller is alpha. So, a x equals to b alpha. So, this relation we used here, we can use. So, using these things we can solve the problem. So, you will see that a x and alpha their sign will be peculiar, because when a x will be rightward, then this wheel will rotate in the clockwise direction, but our positive direction will be anti-clockwise direction. So, in that case we can adjust the B, we can make negative sign and this way you can adjust, otherwise sign convention will be, you can take any convention and follow that. Next, another problem, let us consider a bar is rotating about a fixed axis. So, it is released, the slender bar of mass m, it is released from the rest in the horizontal position. So, we have to find out the bar's angular acceleration and force exerted on the bar by support A, we have to find out. So, here the how we will proceed? Here we have to use the free body diagram and determine the angular acceleration, because this bar is there, its angular acceleration, because here Newton's law you cannot apply, because it is a rotating bar and unknown reactions are there at A, and so let us see the how we can write. So, this is the free body diagram. So, this in the fulcrum two forces are there, A x and A y in the along the x axis and y axis, and G at G is the C G of that bar. So, the downward force is exerted on the bar. So, equation of motion will be A g equals to, that means center of gravity of the bar, we will have only two components, A g and A y. So, we can write as A x I plus A y j. Now, the its f x all forces along x axis, that means A x equals to m A x. So, force is A x component along x axis, if A x is the acceleration of the bar, so m A x, and y direction acceleration, linear acceleration is A alpha y. So, m alpha equals to A y minus m g, that means in y direction. So, the equation of angular motion about the fixed point A is m A, that means the moment will be L into m g, because C g is in the half length of the bar. So, half L into m g, that is equals to I A. I A means that is moment of inertia about the end A. So, into alpha, alpha is the angular acceleration, but this moment of inertia about center of mass equals to I equals to half m L square, and this parallel, by using parallel axis theorem we can find out the moment of inertia about end A. So, equals to I plus d square m. So, this way we can find out. So, substituting these equations we can find out the angular acceleration, but still the acceleration component A x and A y are required to be determined to find the reaction at A x and A b. So, this is done by one kinematic relation. So, A g, that means center of gravity velocity equals to that end velocity A plus angular, the acceleration of the center of mass equals to linear acceleration of the point A plus tangential acceleration and radial acceleration, these two components are there. So, if the so this is the expression, but we know that when it is released, the omega, that means angular velocity is 0, and that is supporting point, there is no acceleration. So, A is equals to 0. So, we can write A g equals to A x plus A y I equals to alpha k. So, we can write these things, and then if we equating the component of I j, then we can find out A x and A y. Now, substituting these accelerant components into Newton's second law, we can find out the other values. So, this way we can, so the kinematic relationship between the bar's angular acceleration and the acceleration of the center of mass in a less formal way could have been determined in different ways, and G describes the circular path about A. So, we know that the tangential components of its acceleration equals the product of the radial distance from A to J. So, this way we have used these conditions. Now, we are taking another case, that where the motion of a rigid body undergoing general planar motion. Planar motion means here it is rotation and translation both. So, in this case we will use this two equation motion, that is sigma f equals to m a and sigma m equals to I alpha. So, there will be more unknown quantities than equations, and so whatever we require we have to use kinematic relationship. Here one bar is shown, it is sliding, and because it is supported at the wall and the supported by the wall and the floor. So, but smooth, it is a smooth floor and wall. So, this it will slide gradually. So, omega is the angular velocity at rotation. So, the slender bar of mass m in the figure slides on the smooth floor and wall, has counterclockwise rotation, which is shown as omega at the instant shown. What is the bar's angular acceleration? We want to find out. So, here again the approach is, first we have to draw the free body diagram of the bar and apply Newton's second law and equation of angular motion. So, with this we can find out, and then we will go for the other equations, that is kinematic equation. So, here first we have to draw the free body diagram. So, we have shown the reactions, that means from the floor N, from the wall P. So, this is shown on the bar. Now, we have written the equations, that means center of gravity, its acceleration is x I plus a y j, and the force component F x and F y are P equals to m a x. P is the horizontal, that means from the wall whatever force is the P, and n is the normal force. So, we can write these equations of motion, and moment about the C g we can find out. So, moment also of the bar about the C g equals to I alpha, moment of inertia is the I, and this n and p will create some moment. So, total moment equals to I alpha. So, this way we can find out. Now, kinematic relation, here the acceleration of the end points of A and B are not known, but we know that regarding these 2 points, contact points, we do not know the value, but we know that this in the wall that acceleration is perpendicular direction, and in the floor the acceleration is in horizontal direction. So, with this information we can first we write the acceleration of the center of mass as acceleration of point A, then from point A we go to the we can find out the other accelerations like tangential and normal acceleration, and then A g has 2 components we know, because it is a planar problem. So, A x and A y, and right side also we put all these things and we compare the elements of j component, and this way we get the A y, and then we find out the A g. And so, A x we can find out, and moment of inertia I we know. So, bar's moment of inertia from using that thing we can find out the alpha from this angular acceleration. So, this way you can do. So, why do we express the acceleration of the center of mass g in terms of acceleration of A and express the acceleration of g in terms of acceleration b? Doing so resulted in the equations allowed to solve the problem, but those steps introduced into our formulation the effects of, because these we used because the nature of the motion, that means when in the floor the bars the contact point moves in the vertical direction, and in the floor it is horizontal direction. To give that condition we are using that. Now, this type of problem for connected rigid bodies also we can use this planar motion. Here it is shown that one slender bar in the figure of mass m is pinned at O to a metal box MB of mass MB that rests on the smooth level surface. The system is released from rest in the position shown. So, what is the bar's angular acceleration at the instant of release? So, here the same process we have to go. First we have to draw a free body diagram, then apply the equation of motion of the bar and block, then relate the acceleration of the bar center of mass with the angular acceleration of the block, and then we complete the solution. See, here free body diagrams are drawn for both bar and the mass, then block, and these are the equations, and then we want to find out the acceleration of g. For that we have to we start from a, we have to find out that thing. So, a g we assume that a x and a y are the components of the center of mass, two acceleration components, and Newton's law we apply for this bar equals to a x equals to m a x and a y equals to m g equals to m a y. So, a y minus m g is the force along y direction, and if a y is the component, a y is the y component of acceleration, then m a y is the acceleration. So, from Newton's second law we get these equations, and now for angular motion, total moment of that thing we can find out what are the forces, and from that moment total moment equals to I into alpha. Alpha is the angular acceleration, I is the moment of inertia about the c g. This is for the bar, and then we go for the block. That means that block has also two equations for Newton's law, f x equals to minus a x, m b is the mass of the block, and a is the velocity because it is connected at point A, and n is the normal force on the block, and m b is the mass, g is the weight. So, this way, as there is no motion in the vertical direction, no acceleration. So, that is why the force equals to, that means total force equals to 0. And kinematic relation you can find out. So, by a g equals to a plus, so from one end we go to the one end's velocity we know, then we know the two components, that means radial component, radial acceleration component. A g is the acceleration of the center of mass. So, that is equals to the acceleration vector of point A plus angular action, that is tangential acceleration and radial acceleration. These two components are added, then we get those equation, and if we equate this. So, this thing we apply on this thing, a equals to you simplify and find out, and comparing the both sides of I and j, and a x equals to a minus half alpha cos theta and a y equals to minus alpha sin theta. So, by this we can find out alpha equals to this relation. So, here in this example the approach used is applicable to analyzing the planar motion of the broad class of machine consisting of interconnected rigid bodies. Here the block is constant to move horizontally, and block and bar have some same acceleration at point A. That is why when you have found out the acceleration from point A, we know from A we have added the radial and tangential acceleration, and we have found the other points. So, today this planar rigid dynamics, rigid body dynamics, these following things we have covered, that is force linear momentum relation for a system of particles. Then we have extended for rigid body, moment angular momentum relation for a system of particles. Again we have applied it for rigid body, equation of angular motion of a rigid body rotating about a fixed axis, that we have done, and equation of motion of a rigid body in general planar motion, where rotation and translation both are there, and we have used these principles for solving some problems. Now, for studying we can refer the following books. So, here 5 books are there, they are very reputed books. So, these books can be consulted for better understanding of the subject. Thank you.